Today, I'm gonna introduce research trends on my research interest, lithium-sulfur battery. Lithium-ion batteries have become prominent over the past few decades. The highest energy density of lithium-ion battery is approaching its limit at present, but cannot satisfy the requirements of emerging electric vehicles. The capacities of the current NCM-rich transition metal have a limit of around 275 mAh per gram, and the capacity of the graphite anode is also limited to around 370 mAh per gram. Therefore, alternative cathode and anode materials that offer higher capacities need to be developed. Sulfur, one of the most abundant elements offering a high theoretical capacity of around 1675 mAh per gram, has conversion reaction with lithium which has theoretical capacity of 3860 mAh per gram. A simple calculation of the theoretical energy density shows a huge difference of lithium-ion battery and lithium-sulfur battery. Let me briefly explain the mechanism of discharge profile of lithium-sulfur battery. Discharge curve is divided into 4 stages, some of which has two-phase transition from solid to liquid or liquid to solid. According to Gibbs free energy phase transition, a plateau is formed when the phase changes from solid to liquid or vice versa. However, there are challenges to be addressed for high-performance lithium-sulfur battery. Lithium polysulfides, which are generated during the conversion reaction, are soluble in the most common organic electrolytes used for lithium-sulfur batteries. Driven by the concentration gradient force from the cathode to the anode, the soluble polysulfides migrate to the lithium anode, where they are reduced to insoluble Li2S, resulting in an irreversible loss of active material and passivation of the anode. Also, both sulfur and Li2S are insulators of electrons and lithium ions, and this directly limits the electrochemical reactions, resulting in low utilization of the active material. The density of cyclooctasulfur is higher than that of Li2S, resulting in a large volume expansion, approximately around 80% upon lithiation. Since research on lithium-sulfur batteries has been conducted to improve the conductivity of sulfur through the introduction of a carbon composite to a cathode of the lithium-sulfur battery to overcome these disadvantages. However, no material has yet been found for the commercialization step capable of efficiently suppressing the diffusion of the polysulfide intermediate. Research on the cathode, which is a key material that determines the performance of lithium-sulfur batteries, is continuously required and progressed. The core patents mainly focus on a method of storing sulfur directly in a carbon nanotube and a method of generating a secondary structure. Unlike core patents, my experiment focused on expected effects through carbon nanotube surface modification. An element capable of improving the reaction rate of the polysulfide intermediate was introduced to the surface of the carbon nanotube, and an organic material capable of suppressing the diffusion of the polysulfide intermediate was used. In terms of the use of organic matter and the modification of the surface itself, it created a difference from the core patent in the synthesized method, and it was confirmed that it was a differentiated study by deriving excellent electrochemical characteristics.